Starting off with Chapter 9, we want to talk about the physical properties of gases.
Okay, so what we actually want to get in talking about then is talking about gases. And what we're going to start off is talking about what is a gas. And gases are one of our phases of matter. And here I have a diagram depicting the atoms or molecules of each of our phases of matter for solids, liquids, and gases. And these three different phases of matter are distinguished in whether the movement of molecules and whether or not how close together those molecules are. So solids are rigid. The molecules are all touching each other and they have restricted movement. This is why solids have structure, right? Because the atoms have structure, the molecules aren't moving around. So that's why a solid can say support weight, because the atoms are in place and they can, support whatever's placed on top of them. In liquids, you start to get more motion. The molecules are still close together. They're still touching each other, but they have much more free movement. Not totally unrestricted because they've run into other molecules more frequently, but they're still all there. And when you move into gases, now it's just basically a free-for-all. The molecules do not touch each other and have totally free movement. One of the impacts of that is that gases are mostly empty space. In the case of solids and liquids, we call those condensed phases because the atoms are touching each other. In gases, they're fully far apart. They're not touching at all. They're just kind of floating around freely, mostly empty space. So in a gas, it is mostly nothingness in between atoms or molecules, whatever, are making up the gas. So what we want to talk about then are some of the physical properties or the ways that we characterize a sample of gas. That's a lot of what we're going to talk about, especially in this first set of videos. So the first physical property of a gas is going to be amount. So a sample of gas has a certain number of molecules. So generally when we're talking about a gas, we care about what the moles of gas we have, because that gives us an information as to how many objects are floating around in our sample of gas. We can certainly use molar mass, like we have previously, to convert that into mass of a gas. So gases do have mass. It is mostly empty space, but there is still particles in there. There are still things in there. The difference is that gases have just really, really low densities. So for example, air is just over 1 gram of mass per liter, whereas water is a kilogram of mass per liter. So liquids and solids have on average 1,000 times higher density. There's 1,000 times more stuff in that volume, kind of a rule of thumb in terms of the order of magnitude for those densities. So gases do have mass, just very, very low mass for the volume that they fill, very low densities. All right, so beyond just the number of particles, we're also going to talk about the volume of a gas. And volumes of gases is the space that the gas occupies. So we've talked about volume before. We've used volume for liquids and solids. And what makes gases unique from those solids and those liquids is that gases are what we call compressible. So compressible means that you can take a sample of gas, a given number of atoms, and you can change its volume. And this is really unique for gases that does not happen for liquids and solids. If you have, say, a solid, say a book, and you press on it, you don't change the volume of the book, or even say water, right? You can't, it's hard to squish, say, a water bottle. If it's empty, if it's full of air, all of a sudden it becomes much easier to compress that bottle. And so when we have gases, we can compress them, which is unique, because and the reason why we can do that is because they have all that empty space, right? The atoms it's easy for the molecules to just get closer because they're already really far apart. The other thing that comes from this is that if you allow gases to expand, they will. So in this animation, when the piston goes down, the gas molecules will get closer. And when the piston is going back up here, you see the molecules just spread out naturally. There's no force causing those molecules to expand out and fill their container, but that's a unique property of gases. So on the one hand, they can be compressed, and on the other hand, they do free expansion without any sort of force. You don't have to push the molecules apart. They just naturally will flow to be apart from each other. The next physical property we want to talk about is temperature. And this is something we've seen before, right? When we talked about back in chapter 5, thermal energy, the idea that temperature represents the average kinetic energy of gas molecules, how quickly those molecules are moving. And any temperature for any gas always corresponds to the same average kinetic energy. So kinetic energy is all about motion. So higher temperatures correspond to molecules that are moving more rapidly. The molecules are moving around at higher average speeds. So we know higher temperatures means molecules are moving more. So cool gases, the molecules are all still moving freely, kind of bouncing around, just flying around. But at low temperatures, they're just not moving as fast. They're not restricted in how they're moving, just moving more slowly. And at higher temperatures, just moving faster, bouncing around randomly. Generally, when we're dealing with gases, we're going to use Kelvin as our temperature unit, which is a capital K. We're still going to talk about gas temperatures in terms of degrees Celsius, but we're going to start to do algebra with temperatures. And whenever we're doing that, the temperatures will always need to be in Kelvin as the temperature unit. The reason why is that Kelvin is what's called an absolute temperature scale. What that means is that 0 Kelvin is the coldest possible temperature. There are no negative Kelvin temperatures. So one of the things we can start to ask is, well, what makes something the coldest possible temperature? Right? We've said that temperature is about the average motion, how quickly things are moving. So 0 Kelvin corresponds to no motion. That's why you can't have negative Kelvin temperatures, because that would be negative average kinetic energy, and that'd be impossible. You can't moving backwards, still moving. 0 Kelvin is the coldest possible temperature, and there are no negative Kelvin temperatures. So temperature, if we want to go from degrees Celsius to Kelvin, it's just going to be an additive conversion. So 1 Kelvin temperature change is the same as 1 degree Celsius. If we ever want to go from Celsius to Kelvin, we just add 273.5. What that also means is that 0 Kelvin, the coldest possible temperature, is negative 273 degrees Celsius. Technically, it's 273.15, but generally you don't need the 0.15. Celsius is not an absolute temperature scale. It is a relative temperature scale. So 100 Celsius is a higher temperature than 50 degrees Celsius. So that is what makes it relative. But you can also have negative numbers. So most other measurements are absolute, like distance. You can't have a negative distance. That's what makes it a absolute scale. But Celsius is degrees Celsius and degrees Fahrenheit are both relative scales. So absolute, something like Kelvin, 100 Kelvin is double the temperature of 50 Kelvin. That's what makes it absolute. Whereas 100 degrees Celsius is not double the temperature of 50 degrees Celsius. It's just 50 degrees higher. If you want to figure out the actual relative change, you need to convert to Kelvin, because in Kelvin, you can actually look at those absolute changes because you're looking at the actual measurement of the kinetic energy. 0 Kelvin is no kinetic energy, and then you just keep going up. For Celsius, if we want to convert into Kelvin, we add that 273, so 50 becomes 323, 100 becomes 373. And then we can take that ratio and we see 1.15. So 100 degrees Celsius is 15% higher of a temperature than 50 degrees Celsius. Another thing to kind of note in terms of the language, you'll note when we talk about Celsius, it's degrees Celsius. That's another sign that it's a relative scale. It's just Kelvin. It's not degrees Kelvin. It's just Kelvin because it's an absolute scale. All right, so the final physical property of gases we want to talk about is pressure. And technically pressure is force per unit area. So force meaning collision, pushing something over some sort of area. And where this comes from with a case of a gas is the fact that gases, those molecules are moving around, right? Everything we've just kind of zoomed in on the molecules moving around. But eventually when those molecules are moving, they're going to hit a wall. Okay. Whatever container that gas is held in. Is the gas in a balloon? Is the gas in the atmosphere? In which case you are the wall, right? You're the container that gas is colliding with. And so those gas molecules are really small, but there's a lot of them and they're moving pretty quickly. So when they all collectively together are colliding with the walls of the container, they can push the container to move. And so pressure is that sort of how much force is pushing that container to move. So if you have a flexible container, say like a balloon, it will expand, right? When the gas inside of there is pressing, it has a higher, it's pressing via its pressure, it'll cause it to move, right? It causes an expansion or compression. So gases can exert force just by the molecules moving around. And all of pressure is going to be driven by these molecular collisions. More collisions, harder collisions, the molecules moving faster will all correspond to higher pressures, just more energy, more force applied to those walls. when it comes to measuring pressure units, there are a ton of units. So if we want to think about how we measure pressure and the types of units we use, we'll start by talking about atmospheric pressure. So atmospheric pressure, that's the pressure exerted by air, right? The atmosphere around you. There are molecules in that gas that are moving around, that are colliding with you. And so there's some sort of pressure caused by that. And the initial way that this was measured was via a mammometer. This is the mammometer. This is measuring pressure in what's called millimeters of mercury. So literally what you do is you take a dish, you fill it with mercury, right, which is a liquid metal. Then the gas in the atmosphere is going to press on that liquid, causing it to move up this glass tube that is submerged in the mercury. And so the more that is pressed, the more the gas is pressing on the surface of the dish, the higher the mercury can go up. And if you set this up with mercury in a dish, atmospheric pressure on average will be about the mercury will go up about 760 millimeters. So the original unit was millimeters of mercury. This is still actually a common unit of distance of a liquid flowing up, being pressed up some sort of tube. Inches of water is pretty common. That's used by the United States Weather Services and like forecasting and stuff like that. Inches of water is really common, also on boats in nautical settings, but there's also water, feet of water, millimeters of water, all sorts of distances of water. From that, we have gone on to a lot of different pressure units. So the most common pressure unit that we're going to use, that's most common in the chemistry lab, is atmospheres, or ATM is the unit. And the idea of this is that 1 ATM is approximately equal to air pressure at sea level at 0 degrees Celsius. 1 atmosphere would be the same thing as your 760 millimeters of mercury. And so this is really common when you're dealing with gases, especially that are under room temperature or under ambient conditions, because you're going to be about 1 atmosphere or what you're working in. It's also common to use the bar, 1 bar. This is a common pressure unit in weather forecasting. A bar is close to 1 atmosphere. It's under slightly different temperature conditions, and so it has kind of a different effect. But 1 bar is close to 1 atmosphere. It's also a common one that you see. Torr. This is named Evangelista Torricelli was the one who invented that mercury barometer. So 1 millimeter mercury can also just be called 1 torr. Different people use these different units that are literally the exact same thing, but different people use them in different contexts. Pascal is actually the metric unit for pressure. It's not commonly used, actually. It's really small. 1 bar is 100,000 kilopascals. So oftentimes it's kilopascals or thousands of pascals. Pounds per square inch is another one you may have heard, may be familiar with. This is common in industrial applications, especially in the United States. It's a standard kind of description of pressure: pounds per square inch, force per area. And 1 atmosphere is about 14 and change psi. So all these different pressure units all exist. The main thing you want to be comfortable with is the fact that recognizing that these are pressure units, because different people in different fields, whether you're doing weather, whether you're doing chemistry, whether you're doing biology, scuba diving, welding, and whatever it is, you're going to have different units that are used in those different fields. You just want to be aware that there are a lot of pressure units that exist and be able to recognize them. There are, of course, conversion factors between all of these different pressure units. And I'll just, you don't need to memorize any of these, but you do need to know how to use them, right? This is going back to doing unit conversions way back at the beginning of the semester. We're still going to be using those ideas, and they're going to be coming back up. It's also common, these are metric units. You would get metric prefixes, especially on bar and Pascal, because those are technically metric related units. Millibar is really common, and kilopascals. And that works just like we learned about milli and kilo. But so you can do all these unit conversions. So you could ask something like, how many torr in 1 bar, right? 1 bar is a common measurement. What's that in torr? And it's just going to be a matter of taking these definitions and doing the conversion. Well, 1 bar, I can put that into atmospheres. I can do atmospheres into millimeters of mercury. I can do millimeters of mercury into torr. So 1 bar is 750 torr. So you can do these conversions. This is just a handful of definitions for some pairs. You can look it up also. You have the access to the internet. You could have just looked up how many torr in one bar. If you had then you would use that as a conversion, say for if you had 3 bar as a measurement or something. But one of the things you can start to see with what that is, one of the reasons why we're doing gas at the end here is gases are going to touch on a lot of topics we talked about earlier in the semester, like unit conversions here, stoichiometry is coming back. So we want to kinetic energy. Those ideas are kind of also functioning as a review. So some of this stuff is meant to be kind of review because we do have the final coming up in 2 weeks. All right, so just to review, whenever you're dealing with gas, we're going to be looking at physical properties and changes in physical properties. And so the 4 physical properties that we would want are amount, volume, temperature, and pressure. These 4 properties can describe any sample of gas, and really they can describe any sample of matter. What's unique about gases is how some of these can easily change. Amount, moles of gas, number of molecules, that's fairly constant for any sample. But when it comes to volume and its effect on temperature and pressure, these are really dynamic for gases, right? Because you have all that empty space in the sample, gases are highly compressible, they can grow, they can shrink, and that really helps determines and affects the physical properties and how they can be more dynamic and they can change for a given sample based on the conditions it's under. So all 4 of these are needed to define any sample of gas. They're all going to be related to each other and kind of have some different trends, but they're all going to be necessary to describe any given sample of gas. So with that in mind, some of these we can define, kind of standardize in certain ways. And that's what we're going to be based on what we're going to call ambient conditions. Ambient, like the ambiance, the surroundings that you're in. So ambient conditions are just whatever the natural temperature and pressure for your sample are. And so we can define these, we can kind of characterize and standardize these in what's called standard temperature and pressure, or STP. And standard temperature and pressure is a temperature of 273 Kelvin and a pressure of 1 atmosphere. The idea here is that these values, kind of give you a way to standardize the whole point, what you're looking at. So you could just say, I did this experiment or I did this process at STP, and everyone would know what that means. It also gives everyone kind of a standardized that we can all do experiments under these same conditions and see what it is. I will note 273 Kelvin, that is 0 degrees Celsius. So standard temperature and pressure is cold, but it is still a standard value that we can all hit. These aren't what we always work at, right? All the experiments that you would ever do in the lab, I hope you get to work at room temperature. But this is still something that we can standardize, we can all go to. You'll note volume and amount have no standardized values because they are extensive. Extensive properties depend on how much you have in your sample. And so as a result, you can't standardize those because it would be based on what is the sample of gas you're looking at. Temperature and pressure are intensive properties, so they don't depend on how much you have. So if you have a temperature and a pressure, it doesn't matter how much gas you have, they're always going to be that temperature and pressure. Again, a little more review, some of those properties, characterizations back from chapter 1.